I'm John Rouser. I'm a data scientist at Pinterest, and I'm here to talk to you today about TCP and the lower bound of web application performance. So this is a play in 3 acts with a short prologue and a short epilogue. And the big picture is that this is a talk about how the web works and why it works that way. And I mean that in 2 different ways. It's a talk about how the web works because I spend the bulk of the talk explaining in some detail one of the fundamental low-level communication protocols of the internet and how that protocol puts a lower bound on web application performance. But it's also a talk about how the web works because I'm going to talk a lot about the human story of how the internet was created and how it is governed. So away we go. We begin in 1996 when this person, Stuart Cheshire, wrote a famous paper called "It's the Latency Stupid." So this paper starts with 2 observations, the first of which is that making more bandwidth is easy. So imagine that the only network line that you could get at your house was a 56K dial-up connection, and you had an application that needed more bandwidth. Well, hey, that's no problem. You can just get another line and tie them together, and now you've got double the bandwidth. If you needed even more, you could get 10 or 20 phone lines. You could tie them all together with some kind of crazy networking equipment, and you could get something approximating the bandwidth of a modern DSL connection. And it would be annoying, and it would be expensive, but you can do it. You can manufacture bandwidth. But Stuart's second observation is that latency is different from bandwidth. He says once you've got bad latency, you're stuck with it. To see why that's true, we'll look at an example. Let's say that you live in Seattle, and you want to start a website. And there's this really great hosting company on the East Coast, and so you set up your account with them, and you spin up your new site. And so now to talk to your new site, your messages have to go 3,700 kilometers in one direction, and the responses have to go 3,700 kilometers back for a total of 7,400 kilometers. And the question is, how long does that take to make that round trip? And so think about that for a second. Don't shout out an answer if you know the answer, but come up with a guess in your head. What is the round trip network latency from coast to coast? So to answer that, we'll look at the science first. The speed of light in a vacuum is about 300,000 kilometers per second. It must be true because Google says so. So to traverse 7,400 kilometers at 300,000 kilometers per second takes about 25 milliseconds in a vacuum. But your signals aren't propagating in a vacuum. They're propagating in glass in the form of fiber optic cables. And the index of refraction of glass is 1.5, which means that light travels in fiber at only 66% of the speed at which it does in a vacuum. And so that theoretical limit on round-trip latency, it's not 25 milliseconds. It's more like 37 milliseconds for a signal to go from coast to coast and back. And now that is in a single, unbroken piece of theoretical fiber that's been stretched from coast to coast and back with no networking devices in the way. And so if this is the theoretical minimum, the best we could possibly do, how long does it actually take? Well, from my house over a Comcast cable modem and consumer-grade networking equipment when I lived in Seattle, it took about 90 milliseconds. So we should think about that for a second. Remember, our theoretical round-trip latency in fiber was 37 milliseconds. We're roughly only about a factor of 2 away from that. And the thing is, it's been like this for well over a decade. Cheshire did this exact same analysis in 1996 between Lawrence Berkeley Labs and MIT, and he got essentially the same result, about a factor of 2. And so networking devices are pretty good already, but they are not getting faster. And so truly, once you have bad latency, you're stuck with it. So this is fascinating. I hear you saying to yourselves, remind me, why do I care about any of this? Well, Stuart Cheshire cared about network latency because in 1987 he wrote one of the first real-time multiplayer internet games. And in gaming, 100 milliseconds is the difference between an experience that feels crisp and one that feels sluggish. But you all should care because you are in the business of making applications on the web, and it turns out that network latency matters for web applications. To understand why network latency matters for web applications, we need to understand how the internet works. To understand digital networks, it helps to contrast them with another kind of network, an analog network. So if you go all the way back to the dawn of telegraphy in the 1800s, the earliest electronic communications networks were circuit-switched networks. With a telegraph, there is a single pair of wires, a circuit, connecting the keys at either end. When telephones were invented, it was the same thing. In the early days of telephone networks, there were rooms full of humans who would plug wires into switchboards to make a physical connection, a circuit, between you and the person you wanted to talk to. And that circuit would be dedicated to your conversation. And so if the operator pulled the plug, you would be literally disconnected, right? That is why we still use that word when we talk about connections in digital networks. You'd be literally disconnected. And then later on, we developed these fantastically engineered electronic switchboards. This device is called a crossbar switch. You can see that there are 10 screws across the top and then 10 more across the bottom where you can connect wires. And so there are 100 possible ways to connect the top to the bottom. The machinery in the middle can arrange itself so that you can simultaneously make any 6 of those 100 possible connections. Crossbar switches like these can then be ganged together into something called a CLO network. And with CLO networks combining large numbers of 20 by 20 crossbar switches, you can build a worldwide telecommunication network with millions of subscribers. And up until fairly recently, this is how the telephone system worked. You could pick up a phone anywhere on the planet, dial a number on the other side of the planet, and dozens of little machines all over the world would physically rearrange themselves so that there was a continuous circuit physically connecting you to the phone on the other end. And that circuit would be dedicated solely to your conversation for as long as you cared to talk. And so you can see why long-distance calling used to be so expensive. So that's an analog, a circuit switch network. But with the advent of digital computers, people realize that there's a more efficient way to send digital messages. With digital messages, you don't need to dedicate a given circuit to a single conversation. You can easily break digital messages up into chunks called packets and send each packet through the network separately. And then you reassemble them back into the complete message on the other side. And so if you're communicating with analog signals, people have historically used circuit-switched networks. But with digital signals, you can use a packet-switched network. And once you change to a packet-switched network, you get enormous efficiency gains because you can send many conversations simultaneously over the same network link. To be concrete, here's a simple network diagram. There are 2 sites, one at the top, one at the bottom. Each site has 3 hosts connected to a router. There's a single long-haul circuit connecting the 2 sites. So with a circuit-switched network, only one person at the bottom can be talking to any one person at the top at any time. But with a packet-switched network, everyone can communicate with everyone else all at the same time because their messages can be broken into packets and interleaved on that single link connecting the 2 sites. But there's a problem. There's no free lunch. Because all of the possible conversations are uncoordinated. If everyone talks all at the same time, they can overwhelm the available bandwidth on that single shared link. To make that concrete, imagine a phone line, right? If 2 people are having a single conversation, everything's fine. But if many people are simultaneously using the same line, then they end up talking over each other. It turns out it's really easy to find pictures of Obama on the phone. They can end up talking over each other. And you have almost certainly experienced this on a conference call or on a Google Hangout or something like that. The more people there are, the bigger the chance of collision. So packet switch networks make more efficient use of the available bandwidth, but they need some way to fairly deal with congestion. Dealing with this problem is one of the fundamental research areas in computer networking, and the main point of this talk is to explore the congestion control mechanisms of the modern internet. But before we get to that, I need to lay a little bit more groundwork. I want to talk about the origins of the internet and how all of the disparate sites and networks on the internet come to agreement about how to communicate. So recall our simple network diagram. In the 1960s, there were already primitive packet-switched networks that looked pretty much like this. In 1965, there was a network connecting the Advanced Research Projects Agency, or ARPA, in the United States Department of Defense, with the Systems Development Corporation, or SDC, in Santa Monica. In the 1960s, ARPA funded all kinds of basic computer science research, and they used interactive computers with primitive forms of email to communicate. ARPA also supported the Multics project at MIT and the Genie project at UC Berkeley. And the networks actually looked like this. Each of these systems had been developed locally, and they used different hardware and custom networking protocols. And so there were offices at ARPA with 3 different terminals, one for each of the networks. You couldn't use the MIT terminal to talk to the people at UCB. You had to physically get up from your desk, walk over to the MIT terminal, sit down, log in, and then finally you could do some work. And so we had computer networks in 1965, but what we didn't have was an internet, a network of networks. Until 1965, and then in 1965, the head of the Information Processing Techniques Office at ARPA, a fellow by the name of Robert Taylor, he was sitting in one of these offices with 3 terminals, and he was struck with an idea. In a 1999 interview with John Markoff, he recalls saying to himself, oh man, it's obvious what you do. If you have these 3 terminals, there ought to be one terminal that goes anywhere you want to go with interactive computing. And that idea is the ARPANET, which is where the internet begins. In 1966, Robert Taylor went to the head of ARPA with this idea, and he got funded immediately. Taylor said that the head of ARPA, a fellow by the name of Charlie Hertzfeld, he liked the idea so much that he took $1 million out of the ballistic missile defense budget, and he put it right into Bob Taylor's budget, which is like the most enlightened government funding decision of all time. So in 1968, Taylor had developed a complete plan for a computer network. There is the internet in 1968. The first 4 sites would be UC Santa Barbara, UCLA, the Stanford Research Institute, and the University of Utah. So again, he got funding from ARPA, and a company named Bolt, Beranek, and Newman, or BBN, won the contract to build out this initial network. And if you were a computer scientist, this was an incredibly exciting time. At this point, it was clear that the basic infrastructure of a global computer network, a capital I internet, though that word wouldn't come into modern usage for some time, that a capital I internet was going to get built, but it was not at all obvious what anyone was going to do with it. Specifically, BBN had been contracted to build out the long-haul infrastructure that would get messages from site to site, but the software that was going to run on the local hosts, that was left to the sites themselves. And so in August of 1968, a handful of graduate students and staff members from the 4 original internet sites, they began meeting intermittently in person to try to figure out how the host software for the internet should work. In the spring of 1969, there was a working group of 3 people, and they decided that they should start writing down and publishing the results of their discussions. And it was Steve Crocker who volunteered to write up their notes. And when you think about the task that he had signed himself up for, it is pretty frightening. The ARPANET hadn't even been built yet, but it was clear to everybody involved that it was going to be a big deal. And so here's Steve Crocker. He's a lowly graduate student. And he, along with 2 other people, were speccing out the host software for a multi-million-dollar project to build the world's first global computer network. And so as he was getting ready to publish these notes, he became increasingly nervous. He worried about sounding presumptuous. He didn't want to sound like he was making any kind of official decisions or claiming any kind of authority. Looking back on this time, 30 years later, he wrote, mindful that our group was informal, junior, and unchartered, I wanted to emphasize that these notes were the beginning of a dialogue. It's a very, very important word in the culture of the internet, a dialogue, and not an assertion of control. And so he named the series of memos Request for Comments. It's not a big deal. It's just a request for comments. That's all it is. So here's request for comments number 1, host software. So it's still fun to read. All these years later, they got a lot right, and it's somewhere between comical and painful to see them struggle with issues like escaping binary data, right? Like nothing has changed. Nothing has changed in 45 years. So this document is where the dialogue that is the internet begins. The RFCs document the technical discussions of the internet protocols, and some RFCs have special status as standards that the internet community as a whole has agreed to. And in some conceptual sense, the RFCs are the internet. The RFCs are the technical specifications of the internet, and the way that you change the internet is to publish an RFC and to get people to agree to adopt it. And so the RFC process is how the internet adapts to a changing environment. And the next part of my talk tells one story of how the internet adapted when cracks started to appear in its foundations. Okay, so now the stage is set. I've introduced the main characters, and we're ready to get into the major action. So we pick up the story again in September of 1981, when the modern internet was born. In September of 1981, this guy, John Postel, published RFC 793, documenting for the first time the Transmission Control Protocol, or TCP, in the form that we know it today. The TCP algorithm provides for 6 basic properties, but for the purposes of this talk, we only care about 2 of them, reliability and flow control. So first, we'll look at the reliability. Here's the text from RFC 793. It says that reliability is achieved by requiring a positive acknowledgement from the receiver. If the acknowledgement is not received within a specified timeout interval, then the data gets retransmitted. So to see how that works, we'll look at an example of the simplest possible transaction. This is the canonical client-server sequence diagram, right? Time flows from top to bottom. Messages flow back and forth. So the client sends a request of some sort. Looks like it's an HTTP GET verb. The server sends its response. The client acknowledges receipt of the response. And now the client has the data. The server knows the client has the data, and everybody is happy. I'd like to point out that each of the arrows in this diagram is a packet, right? TCP is a digital communication protocol that works over packet-switched networks. And packets get dropped all the time on the internet. So what if the response is lost or damaged during transmission? Well, hey, that's no problem. The server sets a timer when it sends each packet. And if the timer goes off, it retransmits the response. And now the client can act that retransmit. And we're in the same state that we were before. The client has the data. The server knows that the client has the data. And everybody is happy. So we can see how acknowledgements provide for reliability. But what about flow control? First, like, what is flow control and why do I want it? Networking devices have limited buffers, and when those buffers fill up, inbound packets get dropped on the floor. To ensure that the buffers don't fill up, the receiver needs a way to control the flow of data, to put a limit on how much data the sender can put on the wire at any given time. Here's what the RFC says about flow control. It says flow control is achieved by returning a window with every ACK. Here's the important part. The window indicates an allowed number of octets, that's bytes if you're a network engineer, an allowed number of octets that the sender may transmit before receiving further permission. Or to put it a different way, the window is the amount of unacknowledged data that can be in transit at any given time. So to understand how the window provides for flow control, we'll look at another example. Let's say that during connection negotiation, a topic that I will not talk about in any detail at all, somehow during connection negotiation, the client advertises a 5 kilobyte window and specifies a maximum segment size of 1 kilobyte. What's a maximum segment size? I haven't described that yet. The maximum segment size is the largest amount of data that the network can transmit in a single packet. If any packet is larger than this, it has to be fragmented and reassembled. Fragmentation and reassembly is expensive, so we seek to avoid it. And so the sender promises, I won't send you anything larger than that. So it's like before. The client sends a request. Let's say that the response now is 10 kilobytes. So it has to be broken up into 10 1 kilobyte packets. And since the window is only 5 kilobytes, we can only send 5 of them at first. And then the client acknowledges each packet as it processes it, right? Hack, 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 hack. And then as those ACKs land on the server, each time one lands, the server can put one more packet out on the wire, keeping the window full. And now, as before, the client acknowledges each packet. And now we've sent all 10 packets. They've all been acknowledged, and we're all done. It's just like before. Everybody knows what's going on, and everybody's happy. So that is TCP in September of 1981, at the birth of the modern internet. But at this time, there were 213 named hosts on the ARPANET. In May of 1982, still only 235 named hosts. But about this time, a bunch of interesting things happened. First, Sun Microsystems was founded in 1982, and not just Sun, but a bunch of companies began to introduce powerful workstations based on 32-bit architectures like the Motorola 68000. And then, in '83, BSD 4.2 was released. BSD 4.2 is important because it contained the first widely deployed implementation of TCP/IP. So what happened is you had software and hardware colliding to create explosive growth in the number of nodes on the internet. So here's a plot of the number of nodes on the net over a 10-year span from 1981 to 1991. Here's the same data plotted on a log scale. You can see that it begins doubling every 9 months starting in about 1982. And things were going great until about 1986, when the number of hosts on the internet had grown to 5,000. So that's a 25-fold increase since Postel had published RFC 793. And it's at this time that the cracks started to appear. In October of 1986, the internet had the first of what became a series of congestion collapse events. And in retrospect, it's not too hard to see what the problem was. TCP's window, this window I've talked about, it's allocated 16 bits in a TCP header. And so the maximum window size is 64K. And so if the client requests a large file, the server might jam 64K of data down the pipe all at once. And at the time, the internet was a series of little sippy straws, little wide area sippy straws connecting 10 megabit Ethernets. The original NSF-net links were just 56K lines. And also remember that you've got to walk Moore's Law back 30 years. Memory was much more expensive in 1986, and so internet gateways had smaller buffers. And when a gateway runs out of buffer, it drops packets. And when a packet gets dropped, it has to be retransmitted. And this retransmit timer that I've talked about, that retransmit timer is dynamic. The TCP stack is constantly monitoring the round-trip latency of the connection, and it is adjusting that retransmit timer according to what it observes. But when this happens, it can shock that measurement system. And so round-trip times can jump up so quickly that the measurement algorithm lags behind, and then you're in big trouble. So John Nagel was one of the first people to document this problem. In 1984, he wrote RFC 896, which describes the problem so well, I'll just read you a couple of passages. First, he notes that a sudden load on the net can cause the round-trip times to rise faster than the measurements can be updated. If this happens, and the round-trip time exceeds the maximum retransmission interval on any host, then that host will begin to introduce more and more copies of the same datagram into the net. The network, he notes, is now in serious trouble. Eventually, all available buffers in the switching nodes will be full and packets must be dropped. Hosts will be sending each packet several times, and eventually some copy of each packet arrives at its destination. This is what we call congestion collapse. And this little phrase here is a critical point. It turns out that TCP is extremely persistent in trying to deliver packets. And just due to chance, some of the packets make it through to their destination, which keeps the connections alive. And this is important because it implies a terrible result, that the condition of congestion collapse is stable. Once the saturation point has been reached, if the algorithm for dropping packets is fair, Nagel observes, the network will get stuck in congestion collapse. So Nagel writes all this up in 1984, and he cheerfully notes at the time that congestion collapse is not normally seen on the ARPANET because these systems have substantial excess capacity. Well, that was 1984, remember, doubling every 9 months. So here's the Usenet posting from 1986. Critical congestion, mail messages, that's email messages she's talking about, take 2 to 3 days to be delivered, which is ridiculous. So enter Van Jacobson, our hero, the person widely credited with saving the internet from collapse due to traffic in the late 1980s. So like any good scientist, what does Jacobson do? He sets up an experiment. He had 4 machines on a 10 megabit Ethernet at Lawrence Berkeley Labs, each send a 1 megabyte file to another 4 machines at UC Berkeley. And the trouble is that even though these Ethernets were just 400 meters apart, they were connected with a 230 kilobit microwave link. So any pair of machines could overflow the available buffer on that interconnect, and all 4 pairs together could exceed the available bandwidth by 160%. So what did Jacobson see? It wasn't pretty. So here's a trace. Each point on this trace is a packet. On the x-axis is the time the packet was sent, and on the y-axis is the sequence number of the packet. A vertical line of dots then represents a set of packets that were all sent at the same time, and the sort of faint dotted diagonal line that comes out of the origin, that's the available bandwidth of the interconnect. So things look pretty good at first, right? We jam 40 packets into the pipe, but oops, oh, this packet gets dropped at the interconnect and needs to be retransmitted. So does this packet, it gets dropped too, and then we're off to the races again, but oh, here's another drop packet and another one and another one. And it gets better. Here's a packet that gets transmitted not once, not twice, not 3 times, not 4 times, but 5 times. So quoting Jacobson, nothing in this trace resembles desirable behavior. So at this point, Jacobson had seen the behavior at the root of the internet's congestion problems, and in response, he crafts what we know today as the TCP slow start algorithm. So we've already talked about the window that's maintained by the receiver that provides for flow control. But that is not enough, Jacobson observes, and so he introduces another window known as the congestion window, which is maintained by the sender. And before, when I said that the window was the maximum amount of unacknowledged data that can be in flight at any given time, well, now it's the minimum of the regular window and the congestion window that limit how much data you can have on the wire. So the congestion window is controlled by 4 very delicately intertwined algorithms, and the precise nature of these algorithms is an area of ongoing research. There have been many proposed algorithms with goofy code names like Reno and Vegas and New Reno. There's something called Vino, which is a combination of Vegas and Reno. Linux kernels, modern Linux kernels use something called Cubic, and Microsoft with Vista, and I don't think this has changed. With Vista, they completely rewrote their TCP stack using something called compound TCP. I think that's still the case. So there's an enormous amount of variety out there, but what I'm going to describe first is what's documented in RFC 2851 and 3390. And the good news is that slow start, the one part I'm going to talk about in detail, it hasn't changed a whole lot since the late 1980s. So here's how slow start works. First, the sender initializes the congestion window to some number of full-size segments. Until recently, that number was 3 segments. And then every time the sender gets an ACK, it increases the congestion window by 1. And this results in the congestion window opening exponentially. So we'll look at an example of how that works. So it's like before, the client sends a request, but now the congestion window starts at 3, and so the server can put only 3 packets out on the wire. The client acknowledges each of those 3 packets, and for each acknowledgement, the server increases the congestion window by 1 full-size segment, and so now the congestion window is 6. So the server sends 6 segments, the client acts each of those, making the congestion window 12, and by now you can see that the congestion window opens exponentially, right? It doubles every round trip. So this is what's known as the TCP slow start algorithm, and it turned this into this, which is better. So in June of 1988, an implementation of TCP slow start was released to the world in BSD 4.3. In November of 1988, Van Jacobson and Michael Carrolls documented all this work in a beautifully readable paper called Congestion Avoidance and Control. And slow start was codified as an internet standard in 1989 with RFC 1122. Here's the text from 1122. It cites Jacobson's work and says that a TCP must implement this algorithm. And since then, every TCP stack has. So now we've arrived at Act 3. And finally, the culmination of my thesis is at hand. 147 slides and 28 minutes later, TCP slow start means that network latency strictly limits the throughput of fresh connections. After RFC 3390, in the first round trip, you can get only 3 packets. It doesn't matter if you have infinite bandwidth. TCP slow start says you're only getting 3. Hey, no problem, you say, I'll just send really, really big packets. Well, modern Ethernet limits you to packets of 1,500 bytes. So if you take away 40 bytes for the TCP and IP headers, you're left with 1,460 bytes. And so in one round trip, with an initial congestion window of 3, you can get a maximum of 4,380 bytes. Hey, whoa, no problem, you say. I'm running a web service, and I've got HTTP 1.1 persistent connections, and slow start only affects the first hit. Well, recall Yahoo's research from 2007, where they maybe is Steve, I'm not sure, where they found that 1 hit in 5 was from a browser with an empty cache. So for them, for Yahoo's front end in 2007, at least 1 hit in 5 was a first hit. More generally, if you know your average session length and you make some assumptions that are here in the fine print, then you can guess that your fraction of first hits is 1 over your average session length. So it's probably difficult to escape this problem. But no problem, you say, it's only 5 round trips until the window's fully open. And you'd like that to be true. I said that the window field is 16 bits wide. 2 to the 16th is 64K. You divide that by a maximum segment size of 1460, and you get a maximum window size of 44 segments. And if the congestion window doubles in size with every round trip, it's only 5 round trips before you're shipping a full window. Except maybe not, because of the delayed ACK algorithm. What's the delayed ACK algorithm, you ask? The delayed ACK algorithm was introduced with RFC 813 in July of 1982. Here's what the RFC says. Basically, excessive ACKing is wasteful. To see why, we'll look at another example. Let's say that you're running an SSH session and you're going to change directories. You're going to type CD. So you type C, and that C gets fired off to the server right away, and the server ACKs that packet instantly. This is something I've glossed over so far. Both sides of the connection are sending acknowledgments. So far, I've only been showing the acknowledgments on the client side, but both sides send acknowledgments. So anyway, the server acknowledges, but immediately afterward, the server is going to have to echo that C back to you. When you type C, the C that shows up on your screen, that's not the C you type, that's the C the server echoes. So it echoes, it sends that C back to you, the client acknowledges that instantly, and then you type the D of your CD, and the whole dance starts over again. The server ACKs, the server echoes, the client ACKs. Now you've typed 2 characters, we've sent 8 packets, and every one of those 8 packets has 40 bytes of TCP and IP overhead. So that seems wasteful. The delayed ACK algorithm says, don't ACK right away. Just wait a little bit, maybe 100 or 200 milliseconds. And maybe there will be some data to send. And what we can do is we can piggyback the acknowledgement along with the payload, because the acknowledgement is just a bit in the header of a packet. And so here's what this looks like with the delayed ACK algorithm in place. You type your C, the server delays its ACK, hoping that there will be some data to send, right? The kernel doesn't know it's operating at a level much below SSHD, right? So the kernel's sitting there waiting. Ooh, maybe there'll be some data. Oh, yes, there is, good. Sweet, so I can piggyback my ACK along with the previous packet. Piggyback my ACK along with the echo of the C. And now the client delays its ACK, hoping that you'll type something else. And you do, you type D. And the client can now piggyback its ACK along with that D. And then the server piggybacks its ACK along with the echo of the D. And then there's this one packet that's left over at the end. So this is better than before, right? We are sending fewer packets and we are using less overhead. Delayed ACK was codified as an internet standard in RFC 1122, and nearly all TCP stacks implement delayed ACKs and have it on by default. It is possible to turn it off. Generally, modern browsers do turn it off, but it's not off universally. So it pays to be aware of this. So there's one more thing you need to know about delayed ACK. The algorithm says when a packet arrives, you delay your ACK, but there's one more rule. If another packet arrives while you're waiting, then you can acknowledge both right away. And since the slow start algorithm updates the congestion window based on these acknowledgments, it interacts with the delayed ACK algorithm. So for our final example, we'll look at that interaction. So like before, the client sends a request. The congestion window is 3, so the server sends 3 segments of the response. The client doesn't acknowledge the first packet, but it does acknowledge as soon as the second packet lands. And then there's this leftover packet that's just sitting there, unacknowledged. Its ACK is delayed. That first ACK lands on the server. Now the congestion window can be incremented to 4, so this is great. We can have 4 packets out on the wire, but there's that one that's left over from the prior round trip. So we can't send 4, we can only send 3. Now finally, we can ACK the one that was left over from the prior round trip, and then we can ACK again as soon as the other 2 land. So 2 more ACKs make the congestion window 6. We can send 6 packets down and get 3 ACKs back, making the congestion window 9. And at this point, you can see that the congestion window isn't doubling every round trip anymore. It's opening more slowly. If you game this out, you see that it takes 9 round trips before you can ship a full window. So to sharpen my thesis, TCP slow start and delayed ACK together mean that network latency strictly limits the effective bandwidth of fresh connections. And we are now in a position to model the absolute minimum latency to deliver a web page of a certain size on a fresh connection. If you assume infinite bandwidth and no packet loss, and an initial congestion window of 3, if your web page is 3 segments long, you can download it in the first round trip. If you can't fit in 3 segments, there is no benefit in getting to be smaller than 6 segments, which is what you'll get in the second round trip. By the third round trip, you can get 12, and then 21, and then 33, and so on. So what's this mean for a real web page? Here's the Wikipedia page for the White House. The HTML for this page is 291 kilobytes. We probably won't have to transfer 291 kilobytes because HTTP supports content compression during transit via the accept encoding header. And so the browser is only going to have to download about 61 kilobytes of compressed data, which will fit in 43 1,460 byte segments, which can be transferred in no less than 6 round trips. Now recall that the cross-country round-trip latency on consumer-grade networking hardware is ballpark 90 milliseconds. And so for someone across the country, those 6 round trips add up to 540 milliseconds. And if you're on a mobile device, you can easily be looking at in excess of 200 milliseconds per round trip. And so with an initial congestion window of 3, the fastest many mobile apps, mobile users can get that page is well over a second. And remember, that's with infinite bandwidth and no packet loss, assumptions that are certainly untrue for a mobile device. And so now we come to the epilogue. When I first started trying to understand the effect of TCP on website latency in about 2009, this had been the state of the internet for 20 years, since 1989. We experimented at Amazon when I was there with increasing the initial congestion window in an effort to speed up the delivery of web pages. But at first I felt kind of queasy about messing with TCP in this way, right? RFC 3390 suggests an initial congestion window of 3. It's just a suggestion, but that had been the default for so long that I didn't really know if there were substantial risks or some kind of hidden downside to starting out with a larger congestion window. Maybe starting with a bigger congestion window would harm some users. If everyone went to a larger congestion window, what would happen? Would the internet fall back into congestion collapse? It turns out I didn't need to worry. At the same time that I was working on this problem at Amazon, there are some other people who were working on it at Google. And they were looking at slow start. And they had conducted large-scale experiments on Google's front end, testing initial congestion windows as large as 42 segments. And thankfully, they were allowed to publish their results. What they found was that they got substantial performance improvements with larger windows, but they got diminishing returns after an initial window of 10. So they published these results in the ACM Computer Communication Review in June of 2010, but more importantly, they also published an internet draft. An internet draft is a precursor to an RFC. So what Jerry Chu and his colleagues at Google did is to start a dialogue within the internet's governing body about increasing the initial congestion window to 10. And an initial window of 10 really does make a big difference in the kind of short-lived, medium-sized transfers that dominate the modern web. So here's a plot like the one that I showed before. The red line shows the minimum number of round trips to complete a transfer of a certain size with an initial congestion window of 3. And the blue line shows what happens with an initial congestion window of 10. Recall that Wikipedia page for the White House that was 43 segments long and took at least 6 round trips to transmit. Well, if you start with an initial congestion window of 10, you can half that time to 3 round trips, which is a pretty substantial win. In February of 2011, a patch was merged into the Linux kernel to set the initial congestion window to 10, and that change was released in Linux 2638 in March of 2011. And finally, in April of 2013, the IETF published RFC 6928, blessing an initial congestion window of 10 as an experimental change. And this is pretty much the end of the story for now, right? Most of the internet is currently using an initial window of 10 with no ill effects. But still, as web pages continue to grow, you have to wonder whether TCP's congestion control mechanisms will have to be updated further, or whether the web will move to different kinds of protocols, like SPDY, for example, as it continues to evolve. So what can we do given this information? It seems like there are a few lessons that you can draw from this. The first and most obvious thing to do is to make sure that you are running with an initial congestion window of 10. As I said, since 2011, the Linux kernel defaults to an initial window of 10. And so if you're running any remotely recent version of Linux on your front-end web servers, you're probably at 10 there. But lots of things can still go wrong, right? Lots of sites have a caching layer in front of their web servers. Does that caching layer screw up the first few packets? What about your load balancers? Do they screw up what happens in the first few round trips? The only way that you can know for sure is to fire up a packet sniffer like Wireshark or TCP dump and to look at packet by packet traces as a web page is loaded. The second thing that you should do is to carefully consider every byte of content. For HTML, this is less important than it used to be in the recent past. With an initial congestion window of 10, slow start squeezes you less than it used to. But still, it pays to be aware of the edges that are imposed by the TCP algorithm. You should try to fit in 10 segments or in 25. If you can't get all of your content down in 10 segments, maybe you can get down just enough HTML that the user can see some result and begin interacting with the page in some meaningful way. But again, if you can't fit your whole page in 10 segments, then think very carefully about what goes into those first 10 segments. So far, I have completely ignored the size of the HTTP request and response headers, but they eat into the bytes that you can get down in your first round trip. So every byte that you use in your session cookie, for example, that's one less byte that you get for your content in that first round trip. If your page depends on external assets like images or JavaScript or CSS that are downloaded from separate domains, it is probably a really good idea to get the browser cooking on those connections in the first round trip. And everything that I have said about slow start applies to the connections that you use to download those assets, images, JavaScript, and whatnot. And so it might be a good idea to think about the order in which you download those assets. You might want to start with smaller images that you can get in one round trip, and then you can have a bigger image that you get in the second round trip. And then fourth, just accept the speed of light, right? Move the client and the server physically closer to each other. This is why content delivery networks exist, and it's why use a CDN was the second of Steve's original 14 rules for faster performing websites. And then finally, there are a couple of larger lessons that I think that you can draw from this talk. So the first is if you're an engineer, there are some parts of the machine that you need to understand, and there are others that you can treat like a black box. And it's different for everyone depending on what you do. If you work at Oracle, you probably need to understand disk drives, right? Block devices just incredibly well. If you're doing embedded systems work, you need to understand power consumption and flash memories. But if you deliver an application over the web, which is probably everybody in this room, and you care at all about performance, which again is everybody in this room, then TCP is not something that you can treat like a black box. I think you really need to understand how it works in order to be maximally effective. If you're planning to build a business or spend a substantial part of your life working on the web, you should understand how the internet is governed. I said this earlier, but as far as culture goes, dialogue is the fuel that makes the internet go. From the very beginning, the people who built the internet chose an open architecture based on multiple layers of protocol. Here's Steve Crocker, the author of the first RFC, reflecting back 20 years later. He says, "We were too scared to imagine that we could define an all-inclusive set of protocols that would serve indefinitely. We envisioned a continual process of evolution and addition, and that is obviously what's happened." In the words of David D. Clark, the internet runs on rough consensus and working code. For formal governance, there's a standards body named the Internet Engineering Task Force, or IETF, that publishes the RFCs. The IETF has written this handy guide for newcomers called the Tao of the IETF. This document lays out the steps you need to follow if you want to publish an RFC. Pretty much anyone can publish what's known as an internet draft. The standards are incredibly low. That's the precursor to an RFC. From there, you go through a bunch of iterations, taking comments, revising your draft, and when you're ready, you convince an area manager to bring your proposal to the Internet Engineering Steering Group, and then you're on your way to publishing an RFC and possibly changing the internet. That the RFC process works as well as it does is completely astonishing. Human history is ugly. It is full of war and misery and conflict. But the internet is like some kind of crazy artifact from the sort of optimistic science fiction future that Gene Roddenberry imagined in Star Trek. Here's Vint Cerf. Hiding in the history of the RFCs is the history of human institutions for achieving cooperative work. And the last lesson is one of humility. So before I started this research, the research that led to this talk, I looked on the people that created the internet as near deities. People like Vint Cerf and John Postel and Bill Joy and Van Jacobson and so many others. And certainly they are some of the greatest engineers who have ever walked the face of the earth. But even they didn't get it right on their first try. Their designs cracked under scale and had to be repaired over a period of years. So you should design for the long term. If you are lucky, your ideas might live for 40 years or more. But you should also accept that if your system is successful, it will have to change in ways that you cannot possibly predict. You simply cannot get it all perfectly right from the beginning. Given the evidence, to take any other position just smacks of foolish pride, the kind of pride that the universe finds a way to punish. That's all I have. Thanks for your time.